As we continue to explore the tools of modern astronomy, we come to perhaps the most important tool of all, and that is light. Now, you probably don't normally think of light as a tool, but to astronomers, in a sense, it's the only tool that matters. Think about it this way. Unlike any other science, astronomy is a science where we cannot go and experiment. We can't go and touch the stars that we're studying. We can't go to the distant galaxies and measure and see how big they are. All we can do is look and see the light that's coming from outer space. So that light is the key to making sense out of this amazing universe. So we need to understand that light as best as we're able to, right? To be able to decode the messages that are being communicated in that light. So let's do that. That's what this video is about, trying to understand the fundamental basics of light. Now, what's awesome is that the light that we see has, in a sense, hidden information within inside of it. Now, we can see this in a typical rainbow, right? When light is passed through a prism, that light is spread out. And so what we perceive normally as white light is actually many, many colors of light that have all been combined together. So this is the first indicator that something deeper is going on with light. When I look at something and it looks like a white light bulb or it looks like a green leaf, there's more there than meets the eye. Now that notion is not new. I mean, people have seen rainbows since the time of Noah, right? But understanding that white light and the rainbow of light are really the same thing really only goes back maybe 500 years. And our understanding goes even deeper, though, with more recent experiments. The well-known physicist William Herschel devised an experiment where he could actually see whether there's light beyond the rainbow that we're used to seeing. So what he did is he shined light, and in this case it was sunlight, right? We didn't have electricity at the time. This is always amazing to me that these discoveries were made before people even had electric lights, right? They were using sunlight. It's incredible. But he passed sunlight through a small opening and then passed that through a prism, and he saw the familiar rainbow. But then he did something clever. He took a thermometer, and he knew that when sunlight shined on a thermometer, it got warm. So he took that thermometer and he put it at different places in the rainbow. Okay, here's red light, green light, blue light. Which of these warms up the thermometer more? And that was a way of measuring how much energy was contained in these different colors of light. And he found it's not the same. Some colors of light contain more energy than others. That was interesting in its own right. Okay, and we'll revisit that later a little bit. That bluer light has more energy in it. But the most interesting thing he did is that he went beyond the red part of the spectrum, where your eye can see all the colors up to red. Well, he put the thermometer past the red, where it didn't look like there was any light there. And he found that the thermometer still got warm when it was put in that part of the experiment. So he concluded then that there must be light that's still there. Even though his eyes couldn't see it, there must be some kind of invisible radiation beyond the red part of the spectrum, which he called infrared light. Now, what's so cool about this is that it was the first indicator that, wait a minute, maybe there's more to light than what our eyes can detect. There's a couple different ways we're going to go with this. Most of our video is going to focus on the science implications of this, but I want to just pause for a second because I think there's a really interesting sort of living analogy here, almost like a parable, right? And that is that as Christians, we acknowledge that there is more to this world than we can perceive with our senses, right? There is, in a sense, a hidden element to reality, a spiritual element to reality. And we can see that there's a precedent for this. There's an analogy or a parable for this in nature, where there's visible light that can be detected with our eyes, but then there are other parts of the spectrum that were previously unknown or undetected. Right? So I think it's a beautiful analogy to think about what remains invisible to us today that we can't see, yet we detect in other ways, right? The spiritual reality that we experience. I think that's a powerful parable that we can take from science and inform our understanding of the spiritual reality that surrounds us. So here's the thing. This infrared radiation, that was just the beginning, right? There's many other parts of the visible spectrum. But infrared is, in particular, a fascinating part of the spectrum. I want to show you this picture. This is the third picture now in the gallery. What this shows on the left-hand side is a picture of a man in visible light. He's wearing glasses, and he has a trash bag over his hands, right? And this is a familiar sight. This is what anyone looks like when you're just walking around in the light that our eyes can detect. But on the right-hand side is a picture of the exact same situation in infrared light. What I want you to notice is that the infrared light passes through different things than visible light. So, for example, you'll notice you can see through the trash bag in infrared light. It just passes right through that thin plastic. Notice also that the man's glasses are completely dark. So in the infrared, the infrared light cannot pass through the glass of his glasses. So it's kind of weird, right? Things that normally transmit visible light can block the infrared, and things that normally block visible light can transmit the infrared. So light, depending on what part of the spectrum we're talking about, can behave very differently and interact with material in different ways. It's pretty cool. Okay, but infrared is just a part of the story. Just a part of the story. The full electromagnetic spectrum was sort of discovered and unfolded over the course of many decades, between the 1850s and really kind of the early 1900s. And what our picture is that all of these things are really the same stuff. We call it all the electromagnetic spectrum. That the light we see with our eyes is really oscillations of electricity and magnetism, which is crazy to think about. But that the frequency of these oscillations, how rapidly they oscillate back and forth, is what determines whether something can be seen by our eyes or whether it can't be. So that frequency can also be thought of in terms of wavelength. Okay, those are kind of interchangeable ways of thinking about it. And you see that represented in this fourth picture in our gallery, which shows the wavelength across the top, showing very long waves on the left and very, very short wavelengths on the right. But then you also see that represented with frequency lower down in the chart, which shows very high frequencies on the right and very low frequencies on the left. So there's lots of different ways of talking about the parts of the electromagnetic spectrum. What I want you to notice, though, I think wavelength is going to be the most useful for us in our class. But what you think about is that these waves, in a sense, have different sizes with their wavelengths, right? Visible light, which our eyes see, is roughly in the middle. And as the wavelength gets longer and longer, we get to the infrared light that was discovered by Herschel. Now, this infrared light comes up in many ordinary applications. I mean, you think about infrared cameras, you saw that. Infrared cameras are used with security cameras, sometimes to be able to see at night. Infrared is also used in remote controls. So when you have that little light bulb on the end of your remote control for a television, that's an infrared light. It glows in light that's just a little further red than our eyes can see. When you get to longer wavelengths, we get to the microwave part of the spectrum. Again, it's the same stuff. It's still oscillating electric and magnetic fields, but now at a longer wavelength, and there's different uses and applications. And so in this microwave region, we have a few applications. One, obviously, is microwaves. at a very specific wavelength of light. When the microwaves oscillate back and forth, water molecules can ride along with those oscillations, and the water gets hot. And so what a microwave oven does is it shoots that specific wavelength of light, electromagnetic radiation, onto your food, and it heats up the water inside your food. So that's why really all a microwave can do is boil water, and it just so happens that almost all of our food has water in it, so it heats up our food. But if you were to put a piece of tin foil or a piece of metal, there's no water in there, and that's when you get the sparking. You're not supposed to do that with a microwave. Microwaves have other applications though too. Cell phones transmit and receive signals in a part of the microwave spectrum. A few centimeters is the wavelength, right? So microwave has application for communication as well as for actually cooking your food. And then when we get to the radio wavelengths, we get to longer and longer wavelengths, and those are used primarily for communication, right? So you have longer antennas like on your car, or maybe a radio that you use to listen to the radio. And that's sending not only voice communication, but also television signals are generally carried on radio wavelengths, things like that. Now on the other side of the spectrum, when you have visible light, it's getting on the shorter side, the blue side of the spectrum. And then when you go past violet, you get to ultraviolet. So now we're getting to higher energies. And when we think of ultraviolet, we probably generally think of harmful UV light from the sun, right? That's one way to think about it. It's higher energy, it's shorter wavelength, it's about the same size as a molecule, so it can actually penetrate a cell and cause cancer in cells. That's why it's harmful. Ultraviolet also is associated with black lights. When you shine a black light and things glow in the dark, that's ultraviolet light that's shining and being absorbed by a material and then re-emitted in light our eyes can see. We go further towards shorter wavelengths, higher energies, we get into the X-rays. Amazing thing. Remember, it's the same stuff, just oscillating electric and magnetic fields, but now the wavelength is so short, it can pass right through materials, pass right through paper and through walls, and even through our skin, but it reflects off of really hard, dense things like our bones, right? So naturally we know X-rays are used for seeing pictures of our skeletons inside our bodies. And then we get to gamma rays. Gamma rays really don't have many applications, but they're very high energy waves, and they are created in deep space with tremendous explosions. Sometimes nuclear explosions on Earth can cause gamma rays. It's something we associate with the general term radiation. When you have a nuclear explosion or nuclear event that has that much energy, you would see the creation of gamma waves. So there's a sense of the full spectrum of light. Again, it's amazing. It's all the same stuff, but different wavelengths and so many different applications that we can see from them. In every part of this spectrum, our universe has things that give off that kind of light. There are things that glow in the radio waves. There are things that glow in the infrared. There are things that are gamma ray bursts, these huge explosions that just shower out gamma rays. We observe bright things in the sky in X-ray light. So we have telescopes that can observe all of these different parts of the spectrum. It's really, truly amazing. Now, one more thing that is on here that it's really worth taking a look at. So we're going to see this several times throughout our course, and that is the bottom part of the graph. It says temperature of objects at which this radiation is most intense, the wavelength emitted. So temperature is also connected to these different parts of the spectrum. We need to make some sense out of that. Now, there's often confusion that infrared light is somehow heat or heat light. And that's really a misnomer, because here's the thing, right? If we go back to a second to the third picture in our gallery, you'll notice that this man's face is kind of glowing in that infrared picture. It seems like he's glowing in the infrared. And he is. But the truth is that everything is glowing all the time. This is kind of crazy, okay? Everything that has a temperature is glowing. So right now, there's probably a light bulb somewhere around you. That light bulb is glowing in visible light, like you can see it with your eyes, because it's glowing so hot, right? If you touch it, it probably could burn your hand maybe. It's really hot. It glows visible. Or you see the sun. It's glowing brightly, kind of yellow because it's so hot. Well, right now, my hands, my face, they're glowing. They're glowing, but they're glowing in the infrared. Because, if I go back to this fourth picture in the gallery here, the infrared is things that are a little bit cooler glow in the infrared. And my body and skin, there may be 70 degrees Fahrenheit. What is that? That's in the, maybe, I'm not good at Celsius. I'm really sorry if Celsius is your familiar unit of temperature. But what would that be? 70 degrees Fahrenheit is like 20 degrees Celsius. Okay, so that's what my skin is like that's the temperature of my skin. And at that temperature, it's glowing in the infrared. As things get colder, they glow in the microwave or in the radio wave part of the spectrum. On the same token, if things get really hot, they glow at the farther end of the spectrum. They glow bluer. They glow in the ultraviolet, even in the X-ray. Some of the hottest things in our universe, this material that's falling into black holes, it's so hot it actually glows in X-ray light. Okay, so temperature is connected to the light that we give off, and it's connected in a very specific way. And that relationship is called Wien's law. And you're going to see this a couple times in our course. So this is another graph. It's another one of those graphs where it's like if you want to impress your friends, say, hey, I'm learning astronomy and it's really complicated. You're going to show them this picture. This is the last picture in our gallery. So let me just orient you to the graph a second. On the bottom scale, we have wavelength, and it's measured in really small units, micrometers. What that means is that 1 micrometer, okay, you see that on there? That's kind of like the infrared part of the spectrum. The important thing you see there is that the colors of the rainbow are labeled. So right there, red, orange, yellow, green, and blue, that's where the visible part of the spectrum is on this graph. On the vertical scale, you see intensity, how much light is shining. And these curves are showing what we call the spectrum. That is to say, how much light is shining at every one of these wavelengths for a given object. Now these curves are showing you the amount of light that's being given off at different temperatures. Now the units of temperature you see here is a capital K, which maybe is not something you've seen before, but that's the scientific unit for temperature that we use in astronomy. It's called kelvins. And it's referenced against 0 Kelvin being absolute zero, the coldest anything can ever get. So roughly, the units of Kelvin is pretty close to Celsius. You know, but it's Celsius basically plus 270 degrees. So when you see 3,000 degrees Kelvin, it's basically 3,000 degrees Celsius. Okay, so we're talking about hot things here, okay? Your stove top, when it glows and it starts getting like red hot a little bit, if you turn it all the way on high, you know, we're at most maybe 1,000 degrees Kelvin. Okay, so these are starting hotter than your stove top. Now what I want you to notice here is that when something is hot, like 3,000 degrees Kelvin, it doesn't give off very much light, relatively speaking. It's glowing primarily in this infrared part of the spectrum, right? But its tail goes a little bit into this red and orange part. So think about this, right? You and I, we're cold. You know, what are we, like 300 degrees Kelvin? We're glowing in the infrared. If we were to get hotter and hotter and hotter and start approaching the temperature of a star, right? We would start glowing in the red part of the spectrum. Yeah? Just like your stovetop gets warmer and warmer and it starts glowing red. And if we got hotter and hotter, two things would happen. One is we get brighter and brighter. Notice that as you go from 3,000 to 4,000 Kelvin, the intensity goes up quite a lot. So that's one thing that happens. It gets brighter and brighter. And notice 4,000 to 5,000, it goes up even higher. 5,000 to 6,000, it jumps up way higher. So as you get hotter and hotter, you get way brighter, like a lot brighter. Now the second thing that happens is that as you get hotter and hotter, the color that you glow moves towards the blue part of the spectrum. So you might start glowing red, but then your spectrum is kind of getting more of the yellows and greens, and by the time you get really, really hot, you might even start to look like you're glowing blue hot, or, like you heard the phrase white hot. That's when you're glowing right here at the top, and you have every color of the rainbow, and every color of the rainbow means it's white light. But once you get past being white hot, you get over here to the other side of the spectrum, and you're mostly glowing in the blue light. So you like blue hot. That's really hot. And ultraviolet hot. So the point is, as you get hotter and hotter, something gets brighter and brighter and brighter, and it gets bluer and bluer and bluer. And that's especially true when we're talking about stars. As we'll see, it helps us learn about stars when we can look at the light that they're giving off. All right, that's probably more than you ever wanted to know about light. But as we'll see, we're going to be taking that information and seeing what we can learn about the universe by carefully studying that light. All right, we'll see you next time.